Hi 7th grade Trailblazers. Here's your only video for this week, the week of September 21st. It's on measurement and math and science. So let's go ahead and get started. Alright, so you guys have learned in elementary school, like you've learned how many pints, how many cups are in a pint, how many this are in a gallon, and you have to understand America is the only country that really uses that kind of measurement system. The rest of the world uses a metric system in most cases, and in science we also use the metric system. And the reason we do that, the reason in science it's so important, is if I'm a scientist in Germany and I'm sharing my work with a scientist in Kenya, and we don't speak the same language, our data should at least have the same measurements so that we can repeat each other's experiments, we can compare results. So we, scientists way back in the day, decided on using the metric system. Why? Because it's easy, and it's based on just the number 10. And we're going to see that if you look on the ladder to the right, it shows a metric system. And it shows in the middle, that's where we have our different units, which we'll talk about in a minute. And it talks about which each prefix means. So these prefixes, like kilo, hecto, deca, deci, centi, milli, they all go in front of our measurements. For instance, if I was going to use meter, it would be kilometer, hectometer, decameter, decimeter, centimeter, millimeter. If I was going to use gram, it would be kilogram, hectogram, decagram, decigram, centigram, milligram. If I was going to use liter, it would be kiloliter, hectoliter, decaliter, deciliter, centiliter, or milliliter. And so we'll get into that a little bit more in depth next week. So using SI is a system, and SI stands for Système International because the French are the ones that came up with it. So in America we would say International System of Units, but it's really called the SI because the French have them backwards. So it allows scientists to compare data and to talk to each other about their results. Alright, so let's talk about the different units of measure. So up until this point in your career, you've probably used inches. Inches are a no-no in science. We use centimeter, we're going to use meters. So a meter stick is the official unit. So if they ever ask you on a quiz what the official unit is for length, you would say the meter. And here, though, we're probably going to work more with, smaller units of the meter, the centimeter. But know that length is measured with a meter. Mass. Mass is the amount of matter an object has, and the basic unit for this is a kilogram. So a kilogram, like if we were going to measure ourselves, our weight would be in kilograms. That's kind of big. Usually in this class, we're going to be dealing with grams, which is just a smaller unit of the kilogram. Alright, a lot of people get mass and weight confused, but they're totally different things. Mass tells us how much matter an object has, how many atoms make up that object. Weight is different. Weight is actually telling us how the force of gravity acts upon that object. So to find weight, it's an equation. It's weight equals mass times g. And don't worry about that yet. If we need to use it, we will. It's super easy, and we'll get into it later. So the basic unit for weight is the Newton, like Isaac Newton, the apple, because remember he was the one that kind of went, oh, gravity. So he's got a unit after him. So we in America would say pounds, like you weigh 15 pounds or whatever, but in science it's the Newton. Alright, there's volume. Volume is the amount of space an object takes up. There's two different types of units for this. So if it's a solid thing, it's the cubic meter, and that's because if you remember doing any kind of volume measurements or math when you were in elementary school, if you were going to find the volume of something, it was probably length times width times height. So that's three things. So that's why it's the cubic meter. Do you see where it has an exponent of 3? That's because it's 3 measurements. The liter is for liquid volume. So if we look at the graduated cylinder, and that's what that's called, a graduated cylinder is the tool we use to measure volume. If you look at that, it's got this weird thing, like how do you read the liquid? Some of you would say you read it from the top of the liquid. Some of you would say you'd read it from the bottom. Some of you might say you read it from the middle. But you actually read it, if you look at the graduated cylinder, you look at it dead on. You have to read the bottom of the dip. So if we were really going to find the volume of that liquid, we would see that this is 6, this is 6.2, this is 6.4, 6.6. So I would read this as 6.6 milliliters. Okay, and that line is called the meniscus. So it's the bottom of the bubble that we read when we look at a graduated cylinder. All right, density is the measure of how much mass is given in a contained volume. And here's the deal with density. There's no densityometer that Miss Marshall has back in her closet for us to measure density. You have to just do math. And the way that you do it is you do mass divided by volume. So if I asked you to find the density of a book, you would have to first find its mass. So you would put it on some kind of scale. And then you would have to find the volume. If it's a book, it's a cubic thing. You can just do length times width times height. You get both of those measurements and you divide. So this cute little heart, this graphic, helps us to remember how to do density. And we'll get into that a little bit more in depth as the year goes on. The unit for this is the cubic meter. Why? What is the unit for mass? Remember, it's kilograms. What's the unit for volume? In this case, it's meter, the cubic meter. So it's just that fraction. That's the unit, base unit. All right, in America, we use Fahrenheit, so lately it's been around, it's kind of cooling off, haha, if it doesn't feel like it, but it's been like 89 degrees Fahrenheit. Yeah, America's pretty much the only place that uses Fahrenheit. The rest of the world uses Celsius. So sometimes on quizzes or in examples, I'll say 25 degrees Celsius, and you guys are like, oh my god, that's so cold. No, that's not cold, because I'm using Celsius. And when you do the conversion, 25 degrees Celsius is a little bit warmer than room temperature. So scientists use both Celsius and the Kelvin scale. And the unit we're going into soon with heat, we'll talk about temperature and those units a little bit more in depth. For time, the unit of measure is a second, so be careful when I ask you to record time. If you record time in minutes, you need to multiply that back out so that you get the seconds. And I'll remind you to do that when we need to in a lab. All right, so let's talk about some math skills that are really important in science. The first one is estimation, and you guys had this on your last quiz. And you learned this when you were younger. You do estimates. They're not guesses. So you just don't guess, I think there's 50 seals in that picture. Instead, you are going to base it on a reasonable assumption. Maybe you just measure a certain part of that box and say, okay, in that certain part, there's 3 seals, but then there's 5 boxes. So if there's 3 seals in one box, but there's 5 boxes, 3 times 5 is 15, maybe there's 15 seals. I mean, clearly there's more than that, but I'm just giving you an example. So they're not based on guesses. Instead, they're based on stuff we know, and then we make reasonable assumptions from that. All right, accuracy and precision are super important. Accuracy refers to how close a measurement is to its true or accepted value. Let me back up for a second. Let's start with the density of water. The density of most substances is known. We know it. You can go and Google it. You can print out a list of density of common substances, and that's what we find every single time. The density of water, pure water, is 1.0 grams per liter, okay, every single time. So if I asked you to find the density of tap water in class, to see how accurate, so you would do that a bunch of times, and maybe you kept getting that it was 0.76, okay, grams per liter. And is that very close to 1? It might sound like it's very close to 1, but in science, 0.76 is not really that close to 1. And you might ask, well, why, Miss Marshall, would our water densities be so much different? Remember I said it's the density of pure water. Is the water that comes out of the tap in our classroom necessarily pure? Probably not. It's going to have metal in it. It's going to have other dissolved substances that would affect the density. Okay, so if I look on my graphic to the right, so if it's accurate, it's not going to be very close to that bullseye. So the bullseye would be that it's accurate. All right, precision means how close a group of measurements are to one another. So maybe I did my tap water a bunch of times. Maybe I did it 5 times. And one time it was 0.76, the next time it was 0.74, the next time it was 0.72, the next time it was 0.78, and I did that the 5 times. And maybe I'm not accurate, but goodness, my results are precise. That means they're very close to one another. So what we really want to try to be, and what we hope our results are both accurate and precise. But sometimes they're just accurate, meaning they're close to what the value should be, Or sometimes they're not, they're precise, but they're not accurate. Like they're really close together, the results we got, but they're nowhere near they should be. And lastly, if we're not accurate or precise, something happened. We need to go back and look at our experiments. All right, to tell if we were precise, we have to perform a calculation called percent error. And I know that you learned this in math, and your teacher teaches you, the wording might be different, and this maybe looks like a scary calculation to you, but it's really not. Percent error is just a division, so it's actual. So what did you get? What did we know the accepted value of water is? We know it's 1. So in our case, we got in that, if I'm doing the equation, I would write down 1 minus, remember my experimental was 0.76, so I would do 1 minus 0.76, that's 0.24, divided by 0.76, so we're going to do that math, and then we get a decimal, and then we just multiply it by 100, and that's going to give us our percent error. So if our percent error is really high, that means that's not good. We want our percent error to be really low. If our percent of error is low, that means we didn't make that much error. If it's really high, then our data is probably not fabulous. All right, some other things I want to go over. I mean, I really think you guys should know these tools, mean, median, mode, and range. But since I expect you to know it, I'm not going to assume that you just do know it. The mean is just another word for average. To find the average of any set of numbers, you just add them up, then divide by the total number added. So pretty easy. Median is finding the numbers in the middle, so you have to put them in order from least to greatest. If you have an odd set of numbers, it works out well because there will be just one in the middle. If there's 2 numbers in the middle, you take those 2 numbers together and you average them to find your median. Your mode is your number that appears the most often, so sometimes you don't have a mode. Sometimes you do, sometimes you don't. Again, having it put in order from least to greatest helps you pick out that pattern. And then the range is just the difference between the greatest value and the least value. And then that graphic on the right is pretty cool. It shows you what to do. All right, so the last slide talks about reasonable and anomalous data. Okay, so if I look at my graph on the left, I'm going to see that most of my data is pretty accurate. It's really close together. It's not super precise, but it's pretty accurate. It's close to the accepted value. That's good. Okay, so I got good stuff. But then I have this green part, this X over here. So that means I have a piece of data, or I had an observation that fell outside of the rest of them. That is considered an anomaly. An anomaly is something that doesn't fit a pattern. So this is anomalous data. It doesn't seem to work with everything. Now what most students want to do is when they get anomalous data, they want to pretend like they don't have it. So they want to erase it off their paper. They don't want to report upon it. They don't want to include it in their results, and that's not good either. You should always include it. You should note it, but you should also understand that you probably did something wrong. There was maybe bias in your experiment. Maybe you looked away for a couple seconds and something happened and you missed recording a temperature. And there's lots of reasons why you can have that anomaly. So when you do your conclusions, you should mention that happened, but really you should base your data on this accurate. Because most of the results in this are accurate. And that's it for this week. Have a good one, guys.